this this part of the lecture we'll try to so let me give you an overview. Okay, so we have a matrix. Okay, last time when we have a matrix in this part of the course we talked about vectors. Okay, vectors, and then we talk about when we combine a bunch of vectors we get to the span, right? And somehow we get a vector space. Another way to obtain a vector space is like you have a set of homogeneous linear equation and you take a solution of them. Okay, you also obtain a vector space. Okay, so part of the course we talk about vectors, how to manipulate vectors, like linear combinations of vectors, stuff like that. Okay, but what we actually concerned about vectors is when what we actually work with vectors is not we won't usually work directly with vector space, but we work with matrices. Okay, so we try to connect matrices to vector space. Okay, so given a matrix, there are 4 vector space associated with it. Okay, so we'll look at it. We'll look at them now. Okay, so if you have a matrix with m rows, n columns, okay, you can have m row vectors. Okay, when you have a set of vectors, you can take its span. Okay, and you get a vector space. Okay, a span of a set of vectors is a vector space. So if you take a span of the row vectors, you obtain what we call row space. Okay. On the other hand, you have n columns. Okay, so if you take the span of these n columns, we get column space. Okay, so these are 2 spaces that are associated with matrix A, row space and column space. Okay, but think about the size of the vector in each of the space. Okay, the row space is the span of m row vectors. Okay, each of these, what is the size? What is the how many elements inside each of these pink vectors? How many elements do we have? It's equal to the number of columns of A, right? So each vector in the row space, okay, is of size n. Okay, so a row space, every vector in the row space belongs to R to the n because each vector is of size n. The length of the vector is of size n. So that's mean the row space is a subset of R to the n. Okay, we'll look at that concretely later. Okay, now column space. Okay, each vector in the column has m elements. So the column space, each vector belongs to R to the m. Okay, so the column space is a subset of R to the m. It's a subspace of that. Okay, so we have 2 space now. Okay, and then I'll show you 2 more later. Okay, but let's take a look at that concretely now. Okay. Okay, so when you have a matrix, what is a matrix? It's not a matrix from the movie. Okay, so it's a matrix. This matrix, you can think of them as many rows of row vectors or many columns of column vectors. Okay? When you have a set of vectors, you can look at the span. So if you look at this perspective, okay, the span of these 4 vectors will be referred to as row space. So that's the span of rows of matrix A.
So you take the rows and you take the span of it, you get row space. If you look at, so the row space of this matrix is span of this vector 1, 2, 3, 4, 5, 6, and 7, 8, 9, finally 10, 11, 12. Okay, and you see that every vector is of length 3, right? So every vector belongs to R to the 3. So this span row space is a subset, is a subspace of R to the 3 because you have 3 elements. Okay. On the other hand, if you look at the span of these columns, we get column space. And it's basically span of this vector 1, 4, 7, 10, and 2, 5, 8, 11, and 3, 6, 9, 12. Okay. And you can see that each vector is of length 4, right? So span is a subspace of R to the 4 because every vector has 4 elements. Okay. So now we have 2 spaces. Okay. So what can we talk about these spaces? Okay. What can we talk about these spaces? Last time we talked about basis. You remember basis? Basis. 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 Okay. When you have a space, you can talk about the basis. Okay. This is like the vector that forms the skeleton of the space. Okay. So we'll look at the basis of the row space and column space of the matrix. Okay. So before we do that, let me show you one thing. Okay. So this is what we just did, but with another matrix. So we can have a matrix and we perform Gaussian elimination and obtain the other matrix like this. And this is in the row echelon form. Okay. I'm not going to tell you how we did that, but you can sort of like at this point you can believe me that we can do that. Okay. So this previously we refer to this as matrix A, and we refer to this as matrix B. Okay. Now, what is the rank of matrix B? What's the rank of matrix B? 3. Okay, because that's the maximum number of rows which are linearly independent, and all these rows are linearly independent because for each if you go moving up, right, you have more columns. Okay, so you cannot write the topmost row as a linear combination of the lower rows. So they are all linearly independent. So since they are all linearly independent, the rank of B is 3. Okay? So this is called the row echelon form. And all the rows are linearly independent. Okay? Because you cannot write it as a linear combination of the others. Okay. And when you have a matrix, you have, okay, we'll come back to that later. So let me try to finalize the rank. Okay. Now, okay. So we know that B has 3 linearly independent rows. Okay. Can A have more than 3 linearly independent rows? Okay. There are 2 directions here. Okay. So let's look at A. Okay. Suppose A has a lot of linearly independent rows. Okay. Suppose A has. So let's think about the thing in this direction. So we start with A and we can obtain B from A. Okay. When we obtain B from A, what we just did? We combine rows of A. Okay. So if we start with, if from A, if we have k linearly independent rows, So you start with k linearly independent rows. After we perform some of the row operation, we get to B, right? Can B has more than k linearly independent rows? You can see that when we have A, right? So let's think about it. Okay, this is A, and some of these like these are the linearly independent rows, and we have some linearly dependent. So the rows down below are linear combination of the top rows. Okay, to get to B, right? To get to B, we just take some of the rows and add them up, multiply something. If we multiply something, it doesn't change the. I mean, all the rows, all the linearly independent rows remain linearly independent, right? But if you take some of the linearly independent rows and add to the bottom section here, like this bottom section remains linear combination of the top rows. Okay, so by taking some of this row and add to the bottom section, you don't change the number of linearly independent rows. Okay, but you can take some of the bottom rows and add to the top rows. Okay, can you create more linearly independent rows? You cannot, right? But maybe you can destroy some of the linearly independent row by, make a mistake and remove some of the linearly independent on the top, right? So by performing row operations from A to B, you cannot increase the number of linearly independent rows. Okay? Because of what? Okay. So you can see that every row of B, right, can be obtained from as a linear combination of the rows of A. Okay. So every row of B has to belongs to the span of this set of linearly independent rows. Okay. So you cannot, basically you cannot create more linearly independent rows from A. Because what you just did, you just add linear combinations of this row over and over again. Okay? So I'll be a little bit hand waving here, but you should sort of like believe me. Okay. ขอเป็นภาษาไทยนิดนึงเพื่อความชัวร์ว่าคุณเก็ตนะครับ ก็คือเราจาก A เรามี k linearly independent rows and เราทำ row operation มาได้ B ใช่ไหมสิ่งที่เราบอกได้ก็คือว่าโดยไม่พิสูจน์ผมแบบข้ามบทพิสูจน์เลยก็คือจำนวนแถวที่มีlinearly independentใน B จะไม่มีทางเกิน A ไม่ทางเกิน K ได้ก็คือเพราะว่าสิ่งที่คุณทำคือสิ่งที่คุณทำก็คือเอาแถวมาผสมกันไปผสมกันมาใช่ป่ะเพราะฉะนั้นคุณไม่สามารถสร้าง independence row เพิ่มขึ้นได้จากเดิมเพราะว่ามันก็อยู่เท่าเดิมนั่นแหละ So you cannot create more linearly independent rows. Okay. So when I say now, I know that there are linearly independent rows in B. Okay. So if there are linearly independent rows in B, I know that K has to be what? At least R, right? K cannot be less than R because you cannot increase the number of linearly independent rows. Okay. So from this direction, we know that K has to be greater than or equal to R. Okay. Now, this argument is really nice because we can use it backward. Okay. From what we discussed previously, we can obtain A from B as well. Okay. By going forward, right? When we do row elimination, when we do Gaussian elimination, we obtain B from A, right? But as we do in the exercise, we can also, given B, we can obtain A. We can, take a linear combination of some of the B rows, and finally we get to A. Okay. So on the other hand, you can obtain A from B. Right? So you start with B,
and we do something, and we get to A, right? So if B has some linearly independent rows, it has R linearly independent rows, and you obtain A, and you know that A has K linearly independent rows. What can we talk about R and K? Can K be larger than R? So we start with B now, okay? We don't start with A, okay? We start with B. B has R linearly independent rows, and we do some row operation. So all these rows are linear combination of the previous R rows. So you start with R linearly independent rows and obtain this. So the number of linearly independent rows in A has to be at most R as well. Okay. So from this direction we can conclude that R has to be at least K. Okay. Now, since we have this and we also have this, what can we conclude? So we can conclude that R equals A, K. So the rank of A and the rank of B is the same. Okay. So if you want to find the number of linearly independent rows of A, basically you can just look at the linearly independent rows of B, and then be done. Okay. ตรงนี้มันจะลอจิกนิดนึงต้องลองคิดตาม You need to come back and think about it for a little bit before you can believe it. But if you don't really want to think about it, you can sort of like believe me that the rank remains the same. But the idea is not that hard. Okay. Alright. So the rank is the same. Okay. This rank, okay, of this row rank, we refer to this as row rank because we work on the rows here, right? We look at the maximum number of linearly independent rows. There is something called the column rank. What is the column rank? The column rank is basically the number of maximum number of linearly independent columns. Okay, so row rank, the maximum number of linearly independent rows. Column rank is maximum number of linearly independent columns. So what is the column rank of B? Now, how many non-zero column of B? 4. But what's the column rank of B? It's not that easy, okay? But it's 3. So let me show you. Now, look, right? Look, now, non, column, now, Okay, so let me show you one more thing. Okay, so previously you talked about row rank. Now we look at column rank. Okay, the column rank. So is this just if you just take these columns, they are linearly independent. Okay. If you add this column, these two columns remain linearly independent, right? Because you cannot make 3 from that, right? But is this column, if I add this column, the yellow one, yes, do the set of these 3 columns linearly independent? No. Because can you obtain this column from this one? Yes, you can, multiply 2 and subtract, right? And you get 3 and UI3, you get to this column. So this column, so out of the first 3 columns, there are at most 2 columns which are linearly independent. You can take this one and that one, or you can take this one and that one, or you can take this one and that one. You cannot take 3 and get the linearly independent columns. Okay. And the third, and this column, if I add it to this set, do they become linearly independent? Yes, because it's 2 here, right? So you can have, you just have basically 3 linearly independent columns. Okay, so the column rank is 3 of B is 3, and you can also show that the column rank of A is also 3. Okay, and this is a fact of linear algebra that the row rank and the column rank is the same. I'm not going to prove it. If you want to see the proof, I can give you the video clip. So last year I talked about it, but yeah, let's try not to.
Proof.
Okay. So the column rank equals row rank. Okay. Okay. So let's talk about row space and column space. Okay. So previously we talked about the number of the number of linearly independent rows and number of linearly independent columns. Okay, they are related to this two space. Okay, so we have, if we take the columns and we take the span of them, we have column space. When we take about row, take all the rows and take the span of the rows, we have row space. Okay, again, take all the rows. Each of the row has length n, right? So the span of row, okay, you have m rows. Okay, this one is called row space, and it's a subset of R to the n, because every vector is of length n. Okay. And if you take the columns, okay, span of column, it's a subset of R to the m, because each vector has m elements. Okay, so that's the two space for that we get from the matrix. And when you have a space which are subset of other space, so row space is subset of R to the n. R to the n is also a vector space. Okay, so we call it a subspace. Okay, so let me show you. So you have this matrix, the column space. Okay, the column space of this matrix is the span of these 3 vectors 0, 1, 2, 1, 4, 3, and you can write it as a set like this. So this is like all the set of all linear combination of these 3 vectors. So that's the span of the column of A. Okay, and you can see that these 2 vectors are linearly independent, and they basically span R squared. So that's the column space. And the row space is a linear combination of the first 2 rows. You only have 2 rows here. So this is the set of the row space. This is a row space. It's a subset of R cubed. Is this row space equal to R cubed? Okay, think about it this way. So you have a vector, the first vector and the second vectors. They are not in parallel. Okay. So in 3 dimensions, the span of 2 vectors, what do you get? You get a plane, right? And they are not equal to the whole 3-dimensional space. So it's basically it's a strict subset of R cubed. Okay. So that's the 2 spaces. Okay. Okay, so before I show you the other 2 spaces, let me talk about the 2 other. Let me give you a quick review on the concept that we talked about last time. Okay, so we have vector space. Okay, when you have a vector space, you have basis. So this is the set of vectors that sort of like generate the whole space,
and also they are linearly independent.
Okay. We refer to as a basis.
In the vector space that we are interested in this course, they have a finite basis. There are some vector space that have infinite size basis that we won't look at that in this course. So what we learn here is that every vector space that we consider in this course has a finite basis. Okay, you have a set of vectors that sort of like can generate a vector space. Okay. So I'll give you the review on what the basis is, and also I'll give you definition of dimension.